Okay, so actually Google has a demo video for regularization. So you can click this. This machine learning crash course for the new developer or new engineer of Google. Yep. So here's a Google's introduction for sparsity. Usually we use L1 norm and L2 norm. It shows why L1 has more sparsity, and usually we prefer sparsity. We prefer sparsity. So here's the key points. First, the L1 and L2 penalize weights. So it prefers smaller weight. L2 penalize the square of the weight, while L1 penalize the absolute value of weight. So L2 and L1 has different derivatives. A derivative of L2 is 2 times original weight, and the derivative of L1 is k or constant. Okay. So here suppose we have 2, 4, 6, 8 features, and we randomly initialize the weight of the feature. So let's see what happens if we train it 5 times, 5 epochs, and we apply L1. First one is no regularization. I switch to English, but it still shows Chinese bug. Anyway, no regularization, L1 regularization, and L2 regularization. And you see, while the training, L1 will prefer 0 weights for some of the weights. And usually we prefer more 0, which means we can ignore the features, totally ignore those features. Right? It's called sparsity or sparse. Okay, so it's the final result. Anyway, all the 3 methods can show that the 7th feature is more important, has negative impact, and then the other 2 are more important. Basically, the 4 are more important, but the L1 will remove the smaller one. I'll prefer some of the feature. It will prefer some of the features, so it's called feature selection. Sometimes it's called feature selection. Yep. Of course, we cannot prove it. There's no rigid proof. So we just try the L1 and L2. So just try and error. That's why still sometimes need human to tune the hyperparameters. So as we have seen it in previous slide, also for L1 norm, you will get a suppose we have a uni norm, you will get a diamond shape here, and you will prefer the answer to touch the diamond area. For L2 norm, it will be a circle, and there's another solution. Remember, we can choose different numbers, LP. And then infinity, if to the infinity, it will be a rectangle, a square, right? Infinity norm. Remember, infinity norm is to select the max value in the vector, So yeah, infinity norm. So we have seen there are many different linear regression algorithms in our scikit-learn cheat sheet, right? Actually, they are all linear regression with different regularization terms. So if we have learned regularization, we immediately learn 3 algorithms. Right? It's a deal, right? Good news. So the first rigid regression is use L2 norm, and lasso is use L1 norm. You can ignore the constant. And if you combine L1 and L2 norm, it's called elastic net. So that's it. Those 3 algorithms just with different regularization terms. So let's see some examples. So we want to predict the house price. Unfortunately, house price usually go up. So difficult to predict, right? But in China, the price is going down rapidly. So eventually at some point is going down. But when the house price go up, you didn't buy a house and you are unhappy. And then you buy a house, the price go down, you are still unhappy. So it's very difficult to be happy. And maybe study machine learning will make you happy, right? Yeah, okay. Then let's go back to Boston house price. House price is continuous, right? It's a number, also it's a regression problem. It's a very old data set, old and famous. So our goal is to try to predict the median price of homes. So it's a very small data set with only 506 samples, because it's maybe, I guess, 50 years ago, 40 or 50 years ago, there were not many houses, I guess. So what's the feature that will affect? What's the feature affect the house price? The crime rate, size, proportion of residential loan, and the industrial loan, I suppose. Yeah, it's industrial loan. Charles River, if it's close to river or not, air quality, number of rooms, and the age of the house, or the distance between the house and the employment centers, tax rate. Teacher is still important for the house price, right? Pupil teacher ratio. Yeah, that's it. So first, for continuous data, we need to we use the one approach to normalize. Before training, we always need to normalize data, which we will like to the mean become 0. So all the data, all the sample points center at the mean. So for continuous data, we will minus the mean, or calculate the mean first, and divide by standard deviation. So that will normalize all, because we have different kinds of feature, right? Different features has different scale, different metric. So we will like all the feature as the same mean, 0 mean. Okay, so make feature center around 0 and have unit standard deviation. That's what we do for normalization. And then we will, okay, note that you can only use the training data to compute to normalize the test data. Suppose you have never seen test data before, you should not use the test data to calculate the mean and the standard deviation. Okay. So yeah, I prepare a notebook again. Let's look at my notebook. Again, the scikit-learn has prepared the Boston house data or house data. House price data, don't know why it's called housing. Download the data and normalize the result. And we can have different regressor. So actually, there's a parameter to set the importance of your regularization term. This is another hyperparameter for the regularization. I just used the default value. Maybe I should set all value to the same. Why elastic net only have one value? Anyway, I use the default value, and you can create a model using scikit-learn. Just use the name linear regression, rigid regression, that's all, and the elastic net. And then use the for loop to try to fit the data. Oh, he fit here. I'll fit the data here. And then you can make a prediction on training data. Also, it's a training result. And remember that the loss function is the mean square error. Also, here we use mean absolute, calculate mean absolute error. I calculate absolute value so we can understand the result better. It basically says that there's a 3.2 standard deviation away from the true price of the house. So let's see the result on test data. They have similar result, but elastic net seems as a slightly better result than original linear regression. Of course, we want to see how the neural network works. You can see neural networks 3-layer works much better than the previous linear regression. Maybe the price is non-linear. Okay, so that's our notebook demonstration. So we have training data 506, test data 102 for different regularization methods. Because I didn't do try and error, I didn't tune the hyperparameters. But with so you can see L1 has slightly better than region. So yeah, in this example, and the elastic net, if you like, you can have 2 regularization turn. Then let's try to predict the house price use deep learning with only 3 layer. Although it has 3 layer, but it has a lot of parameters. So it depends on the size of your layer. And it has already have 5,000 parameters. Around more than 5,000. But it has much more parameters, much more weights, but it can be trained. It looks like it's much better than other linear regression method. Okay. So yeah, maybe I should find an example that traditional machine learning algorithm perform better than deep learning. But in this one, deep learning performs better. Okay, so now I want to talk about a very important spatial regression. It's very important to deep learning, very related to deep learning. It's called logistic regression. It's very special because it's called regression, but actually it's usually used for classification. So it's usually used for, let me see, classification. But the output is still continuous. So it's a regression model indeed. So it's actually linear regression. Plus activation function called the sigmoid. Plus sigmoid function. They use sigmoid function as activation function, right? Remember in neural network, we always need an activation function. So here we use sigmoid function. Actually, sigmoid function was the most popular activation function in deep learning before. And the sigmoid function looks like this one. It looks like a S extend S shape. Somebody says so. I don't think so. Anyway, I don't have better character to describe this shape. So it's called a S-shaped curve. And output is between 0 and 1. 0 and 1. So, and this is the formula. So it has a natural number e to the power of minus x. So why we love the sigmoid function? Because the derivative of the sigmoid function is just the sigmoid function itself multiplied by 1 minus sigmoid function. So it's the derivative is has a very good property. That's why we like. sigmoid function before. However, it's constrained output between 0 and 1, 0 and 1. So in this area, you will have some gradient vanish problem, gradient vanish problem if you use this as an activation function. So how can we convert continuous into binary? Continuous into discrete. Oh, looks good. My writing improved. Anyway, discrete involves binary classification. It's simple. We just end if-else comparison, right? If what? So we just we need to find a threshold. If the original output y, here is a p beta of x. This should be w. It's the parameter, means the parameter. So if the p of x is larger than the threshold t, t means threshold. Oh, yes. Shh. Anyway, you got my idea. So it's usually called T, but sometimes you can call it decision boundary, is the same thing. So if your output is larger than T, then output y prime is equal to 1. Otherwise, sorry, that's y prime is 0. Yeah. So you convert the continuous into discrete. We create a nonlinear. We can create nonlinear with activation function, right? Otherwise, it's just a lot of linear transform. So we can convert the linear equation. The original linear equation is here. Wx plus bias is our original linear regression function, and we put that into the sigmoid function, then use a decision boundary to convert it into discrete. So now we can use it for classification. So we can use it for classification. So maybe I should write classification here. Anyway, so that's a decision boundary. Usually with T means threshold. So how can we choose the loss function? So since we have sigmoid, we cannot use, we better not use the mean square error again. There's another one called cross entropy loss. Cross entropy loss. So basically, the idea behind loss function is to penalize the error, right? Penalize the error. So suppose your original target is 0. What? So this one is y equals 0. Y is the label answer. So if your prediction here, y prime predict. Okay. If your prediction is close to 1, then you have higher loss, right? High loss, high penalty, because the answer is y is equal to, the answer is 0, but your prediction is very close to 1, which means it's a big error, so you have a big loss. So here the answer is y is 1, right? Y equals to 1. So if your prediction here, your y prime is close to 0, then you have higher loss, right? Yep. Huh. So we don't want to use a linear function, so usually we use a log, a log loss. So the loss function, if y is equal to 0, then the loss is y minus p of x. P of x is y or y prime. So as you can see, if it's more close to 1, then if y prime approach 1, then this term approaches 0. And then because it's a minus log, so the loss increase, right? So on the other hand, you just use the prediction for y, for y. So it's called cross entropy. Let me see if I have any. So, okay, I missed an important point. So why is called the entropy? Entropy is from information theory. So Shannon proposed information theory. We want to describe the importance of the information theory. And Shannon found that he think the importance should be in reverse proportion to the probability. In other words, if the event happens more often, then it's less important. It's less important. But it's happen very few, then it's more important. So for example, if you come to my class every week, then sorry, you are less important. Your entropy is lower because your probability is high, right? It's 1 divided by P of x. But if you only come to my class once in whole semester, then your entropy will be very high. Your entropy will be very high. What happens if you never come to my class? Then it's 1 divided by 0, then it's undefined. So if you never come to my class, entropy is undefined. So you will fail. Of course, you're already here. So anyway, so it's the entropy, and it's use a log function, loss function, because log 0 is 1, right? Yeah. So log 1 is 0. Okay. So if 1 divided by P of x is minus log P of x, and then multiplied by the entropy multiplied by your original probability is, this is the entropy. Entropy is the probability multiplied by your information. Your probability multiplied by your information is entropy is actually the expected value. Expected value. Okay. So we have a loss function for if y equals 0 or y equals 1, right? And then we can add that together. Multiply them by 0. So you from this one you can see that if y equals 0, then you can remove this term, right? So you can focus on the loss of this term. So if y equals 1, you can focus on the loss function of So if y is equal to 0, then this term is removed. So you can focus on this one loss function, and vice versa. And this looks like very long term, but the derivative is very pretty. So if you calculate the derivative of the loss cross entropy loss, you will just get is equal to y minus the prediction, y minus y prime plus x. So it's just y prime minus y. So the gradient is very pretty. That's why we love cross entropy function. The ugly term after derivative, after differentiation, then it becomes a pretty derivative term. Okay, cross entropy term. So let's compare L1 logistic regression for the iris flower data set. And then it performs as well as other traditional method. It's good at the 3-layer DNN model.